Dear students, today we will be discussing about emerging solar energy technologies, which includes emerging cell technologies, photovoltaic thermal technologies, solar fuel technologies. Under emerging cell technologies, we will have perovskite solar cells, organic solar cells, dye-sensitized solar cells and quantum dot solar cells. So, attempt of the researcher is to increase the conversion efficiency at lower cost for these solar technologies. So, we will move on. So, first come to the perovskite solar cells. So, this perovskite is calcium titanium oxide CaTiO3 mineral, and it was discovered in 1839 in the Ural mountains of Russia and named after the Russian mineralogist L.A. Perovskite. So, he is here. He is the guy who has first invented. The ability of halide perovskite to convert electricity to light was initially discovered in 1990s in the LED configuration, while light to electricity conversion was reported almost 2 decades later. A perovskite solar cell used organic inorganic metal halide perovskite as photon absorber layer. The term perovskites is used to describe a group of compounds characterized by the general formula ABX3. So, if you see this figure, from that it can be concluded that what is A? A is an organic cation. Its chemical formula is something like CH3 NH3 positive, and B is a metal cation, okay, or inorganic cation. So, it may be SN2 plus or maybe Pb2 plus, or X is a halide anion, okay, maybe Cl minus or Br minus or maybe I minus. Okay. So, if we see its chemical formula will be something like this. It's a perovskite is a semiconducting compound with a direct band gap of 1.55 electron volt. So, why it is so important? We must know the properties of CH3, NH3, PbX3. So, let us see the properties. So, this perovskite is a strong absorption across the visible range of solar spectrum. It is a long carrier diffusion length of 1 micron. It has a weak excitation binding energy of 45 milli electron volt, a low surge recombination rate. The device structure of PSC, that is perovskite solar cell, is derived from the dye-sensitized solar cell, which is abbreviated as DSSC, where the dye material is replaced with perovskite material. In 2009, PSC started with an efficiency of just 3.8%. So, this PSC has recorded an efficiency of 22.1% in 2017. You see how fast it attains a very high conversion efficiency. So, that is why this PSC is one of the fastest advancing solar technology. So, what are different techniques used for making these perovskite solar cells? Maybe spin coating, maybe spray coating, maybe deep coating, or maybe vapor deposition technique. What are the advantages of this solar cell? So, this method of preparation is easy and it has high VOC. So, it is about 1.1 volt. What are the problems to be addressed in order to utilize this perovskite for large scale application? Instability in atmosphere or humidity is a primary concern, and cell area requirement will be large compared to other solar cells, and this lead Pb is toxic. So, this figure shows the structure of perovskite solar cell. As you can see, we will have this electrode gold, then HTL is the whole transport layer, and then we will have electron transport layer, and we will have compact TiO2, then tissue anode, and then glass. So, this kind of configurations is present in case of perovskite solar cells. So, if we see the rising efficiency trend, what you can see it has got quick momentum to achieve a very high conversion efficiency. So, it was started in 2009 and see how fast it attains more than 20% power conversion efficiency. And also we can see current density versus voltage. So, this blue colored line is for forward scan and red colored line is for reverse scan. So, what you can see here, its a conversion efficiency is about 22.1%. So, there are many configurations what you can see, and also you can see the conversion efficiency starting from 2009. Okay. So, in 2007 it attains an efficiency of 22.1%. And this figure shows the comparison of perovskite solar cells with other solar cell technologies. So, vertical axis shows power conversion efficiency and horizontal axis shows years. As you can see, the development of all those solar cells, they are very steadily increasing. But if we look into the perovskite solar cells, you see the rate of increase of power conversion efficiency with time is very high. And this slide shows the maximum photon energy utilization for common single junction solar cells. If we compare these perovskite solar cells and if we have VOC to EG, that is band gap in percentage, and with respect to perovskite, what we can see, this perovskite is having very good photon energy utilization compared to other solar cell material, except gallium arsenide. As you understand, it is having very high conversion efficiency, but cost is very high. So, what we are looking for, we need a high conversion efficiency at lower cost as far as third generation solar cells are concerned. So, we will see now what happens in case of dye-sensitized solar cells. So, in case of dye-sensitized solar cells, it consists of 4 components. First component is semiconducting electrode, second component is dye sensitizer, then third component is redox mediator, and fourth component is counter electrode. Okay. These are the 4 components we require for dye-sensitized solar cells. So, if we need to know how it works, a dye-sensitized solar cell is a low cost solar cell belongs to the group of thin film solar cells. It is based on a semiconductor formed between a photosensitized anode and an electrolyte, a photoelectrochemical system. So, what are the advantages of this dye-sensitized solar cells? It is having lower production cost, it has got design opportunities, it is flexible, it is lightweight, and feedstock available to reach terawatt scale. Okay. Lot of raw materials are available for this kind of cells, and bifacial cells capture light from all angles. So, that is very good advantage of this kind of solar cells, and it outperforms competitor for indoor application. Now, let us learn quickly what is quantum dot solar cells. So, quantum dots are extremely small size semiconductor material. It is also known as artificial atoms. It is a nanoparticle. The size of the dot determines the band gap. Okay. The quantum dot is a 0-dimensional system where electron motion is confined in 3 dimensions. How it works? The light rays enter through the transparent electrode of a quantum dot solar cell onto a light absorbing layer of dots in order to generate electron hole pair. The charged particles then separate and eventually travel to their respective electrodes, producing electric current. So, which is shown in this figure. Okay? This transparent cover, and then solar radiation has to be absorbed, and then electron has to be separated. Okay? So, we can learn this figure as well. So, since we have learned many things about how this semiconductor works, so there is no point of discussing the things here again. So, this is a transparent glass cover, it travels and it absorbs, because that has to be absorbed, then a hole and electron pair will be generated, and then if electric field is generated by providing external voltage, then we can generate electricity. Okay? Now, what are the advantages of these quantum dot solar cells? Due to their tunable property, quantum dots are integrated in various types of solar cells to increase the power efficiency. They are used as alternative to molecular dyes in dye-sensitized solar cells, and cost of fabrication is significantly lower in this case of solar cell. And these nanoparticles which is used here in quantum dot solar cells prove to be promising candidate for scalable, high efficiency and low cost solar cells. Now, come to the PVT collectors. What is the need of these PVT collectors, and what are difficulties associated with PV collector? Okay? So, before we start with the difficulties and then probable solutions, let us have a look about the importance of this part of the system. That solar energy is the most prominent renewable energy sources due to its availability around the globe, which is clearly understood by now. The annual energy potential from solar energy is about 23,000 terawatt yearly. Okay? And this solar photovoltaic technology is widely accepted everywhere. And this figure, what we can see with time, the rise in solar photovoltaic energy generation, you can see here, it is huge. In 2008, it is about 177 gigawatt of energy, which is already produced by solar energy. Now, the spectrum is also familiar to you. It shows the radiation intensity versus wavelength. So, this wavelength visible range is used for PV conversion, and this is the structure of the PV. If we cut the PV module, and we will have this kind of things, like we will have first glass, then we have transparent conductive oxides, TCO metal grids, and then we will have solar cells, then we will have back metal contact, then tether. Okay? And then solar radiation is received here in this absorber or in the solar cell, where a solar cell is located, and some part of radiation is reflected back. Okay? And there are some losses like convective losses and radiative losses, and from the bottom also heat losses will be taking place. So, the amount of heat goes off is significant. So, what are the shortcomings of PV modules? Okay? So, this figure shows the power versus temperature. As you can see here, with increase in temperature, this power decreases. Okay? That is power, means this power delivered by the PV module or PV cells. And this figure shows the effect of temperature on this open circuit voltage and short circuit current. At the same time, we can see the variation of power with respect to the voltage. So, if you follow this blue line, which is at 0 degree C, so VOC is maximum. When temperature increases from 0 to 25, then 25 to 50, then 50 to 75, we can see the sense of VOC. Okay? Since we know that this power developed by the PV cell or module is a function of open circuit voltage, so if this decreases, then power delivered by the PV cell or module decreases. Okay? So, it is a concern. So, how to reduce this effect? Okay? If we can do something by providing cooling effect to maintain the temperature at say 25 degree C, then what we are expected? We are expected higher conversion efficiency. Okay? So, problem is increasing temperature of the module means decreasing electrical efficiency. For single crystalline silicon cell and polycrystalline silicon cells, this efficiency decreases about 0.45% per degree increase in temperature, and for amorphous silicon it is about 0.25% per degree increase in temperature. So, how to overcome the issues faced by usual PV modules? So, one option is by providing cooling effect by using some arrangement at the beneath of the PV module. So, this is a PV module. At the back side, if we make some kind of arrangement which provides some kind of cooling effect, that actually increases the utility of thermal energy as well as increases the electrical conversion efficiency. Okay? So, this photovoltaic thermal system is a combination of photovoltaic panel and thermal collector for cogeneration. So, by doing this, what we can get? We can get improved electrical efficiency as well as we will get some kind of useful heat gain which can be applied for different applications. So, for example, the space heating and domestic hot water generation together constitute nearly 50% of global thermal energy consumption. So, if we can make this kind of management, so we can of course contribute here for providing hot water by using the same PV technology. If we insert one channel just beneath to the PV module. So, the experimental electrical efficiency increases from 9.8% to 12.5% by providing cooling effect in the PV module. Okay? So, if you consider this is the PV module, so some fluid is injected just beneath of the PV module and hot fluid can be taken out from the other end and that can be used for different thermal applications, and by doing so what we can get? We can increase the electrical conversion efficiency. This is another structure that is called honeycomb heat exchanger. So, this structure, what happens? Thermal efficiency without honeycomb is about 27% and with honeycomb it is reported to be 87%. So, this is the PV module and this is just beneath of the PV module. Another configuration is graphite filled PVT. So, here electrical efficiency with graphite is found to be about 7.25%, whereas without graphite it was about 6.46%. Okay? Also, impinging jets for cooling PV has been reported in many of the literature. It is found that air is introduced in one end of the PV and collect from the other end, and this provides a cooling effect to the PV, and as reported an overall efficiency of 54.5 has been achieved by doing this configuration. So, what we have done here at IIT Guwahati, so we have purchased one PV module, okay, and then we have done something just beneath to the PV module and we try to see how this can be used as a PVT module. So, for this arrangement, for calculation or to investigate the performance of this module, what we have done? We have made some kind of arrangement, like we have a pump attached to it a flow meter, so that regulated amount of fluid can be injected through the tubes which is placed beneath of the PV module, and then we will have IV tracer, then temperature gun, then pyranometer, and then data acquisition system to monitor the temperature at different locations. So, this is the photograph of the experimental facility what we have developed at IIT Guwahati, and the kind of instruments used and then their measuring parameters are shown in this table. Like pyranometer is used for global radiation, and thermocouples and data acquisition systems are used for fluid inlet and outlet temperature, PV surface temperature, absorber temperature, ambient temperature, and PV analyzer is used for maximum voltage measurement, and IV curve pressure is used for maximum current measurement, and temperature gun is used for cell temperature. Also, we have developed one indoor facility, because every time we will not get the amount of solar insolation required for testing. So, we have developed a setup so that we can perform the experiments in the lab itself. So, these lights are installed at a particular height that was optimized, and then PV module to be tested is installed here, and then other measurement techniques are installed, and then we will have data acquisition system to measure all those parameters. Okay. And of course, we have IV analyzer from where we can get VM, IM, I, and these two TS and TA as well. So, once we know these parameters, then we can calculate the performance of the PVT collector at different irradiance. Okay. And this is the actual setup photograph what we have developed for the performance investigation of PVT module. Also, we have to know how to calculate electrical efficiency. So, once we know this VM and IM and then amount of solar radiation which is falling on the collector, and then area of the collector. So, this is the area of the collector, and this Z is nothing but watt per meter square. Okay. And this is in volt, is in ampere, and this is in meter square. So, watt per meter square multiplied by meter square will be watt, and at that top also it is watt. So, both numerator and denominator will be watt. So, finally, it is a dimensionless. So, by using this equation we can calculate what will be the electrical efficiency of the PV module, and then we can calculate thermal efficiency once we know this inlet and outlet temperature of the fluid, and then specific heat of the fluid, and then mass of the fluid which is circulated through the tubes. Then we know what is QU, and this part is always known to us because we have a pyranometer and then area is fixed. So, from that we can calculate what is thermal efficiency, and if we have to say about overall efficiency or energy efficiency, it is a combination of both electrical efficiency as well as thermal efficiency. Okay. So, if we add it, it will be something like this, and next maybe we are interested about exergy efficiency of a PVT. So, how we can calculate it? So, EXT out and EXT in. Okay. So, what is exergy in? So, exergy in can be calculated by using this expression, and exergy out composed of two things, electrical and thermal. So, and again electrical part we can use this expression, and for thermal part we can use this expression. Okay. So, once we know this temperature values and then QU, from there we can calculate what is exergy for thermal part, and if we know VM and IM we can calculate what is exergy in the electrical part. Okay. So, by doing this calculation we can calculate what is the exergy efficiency of a PVT module. Also, there is emerging technology. If we develop some kind of substance which can provide uniform temperature and that too stable. Okay. So, that is a very good idea. So, already we have initiated this kind of work. So, work is something like we have collected some kind of biomass. So, for our case it was water hyacinth, and then we have pyrolyzed it at certain conditions, temperature, heating rate, and then holding time, and we have generated biochar, and we have added this biochar with paraffin wax, and we have maintained some kind of proportions, and finally, we have done some kind of analysis, and what we got is a very good composite material for energy storage. So, this material was applied in the PVT collector. So, you can see here how we applied this, and finally, we get this kind of configurations, and we have tested in both indoor and outdoor experiments, and it is found that this is giving a very good result as far as stability and control of temperature is concerned. Okay. So, these two figures shows some kind of properties which is investigated for this analysis. Now, come to the solar fuel technology. So, these solar fuel technologies use sunlight, water, carbon dioxide and nitrogen from the air to produce fuels. Solar fuels technologies are analogous to natural photosynthesis, where plants make fuels from sunlight. The solar energy can be captured and stored directly in the chemical bonds of a material or fuel, and then used when needed. These chemical fuels in which energy from the sun has been stored are called solar fuels. What is new here is not the fuel themselves, but the way that we can see energy from the sun to produce them. The word fuel is used in a broad sense. It refers not only to fuel for transport and electricity generation, but also feedstock used in industry. Now, have a look into this figure, so which represents solar fuel technology. So, what we can see here is sunlight is used to split water into hydrogen and oxygen. So, if we consider H2O, which splits and convert hydrogen and oxygen. Okay. So, energy required for this reaction is given by Gibbs free energy, and it has a value of G is equal to 237.2 kilojoule per mole. Okay. So, this hydrogen can be used as a transportation fuel. Okay. Also, another way of storage of solar fuel is something like if we can store methane, which is easier than hydrogen. So, already we know the water shift reaction or water gas shift reaction, something like H2 plus carbon dioxide, which will convert H2O plus carbon monoxide. Okay. So, this gas mixture is known as synthesis gas, and that can be refined to finally obtain methane. Okay. So, finally, what it will have, carbon monoxide react with hydrogen, it will form methane plus H2O. Okay. So, this methane can be stored. Okay. So, whenever required, so this methane will combust, okay, or we have to provide oxygen, sufficient oxygen for combustion. So, it will generate carbon dioxide plus H2O. Okay. So, what happens now here, this sunlight is used to produce carbon based fuel from carbon dioxide and water. Okay. So, here it is shown here. So, once we have this carbon based fuel, that can be combusted and we can produce energy out of it, or maybe we can generate fertilizer, plastics, pharmaceuticals, synthetic fuel for transportation. Okay. So, here in this case what happens, hydrogen and simple carbon based fuel are used as raw material or feedstocks by many industries, right. So, what I mean to say here, so we can split hydrogen and that can be used as transportation fuel, or we can generate methane and that can be combusted, and again we can generate lot of product out of it. Okay. So, solar fuels, if we talk about, then hydrogen which can be stored, and then second component is methane, like carbon based fuel such as methane, okay, or maybe carbon dioxide or maybe methanol. Okay. So, these two can be stored and that can be applied wherever required for different applications. So, this artificial photosynthesis, in which systems made by human beings mimic the natural process. Okay. So, already we know what happens when sunlight falls. In presence of sunlight, water and carbon dioxide converted to oxygen and fuel. This is something like glucose which is stored in the plant matter. So, reverse what we need to do for artificial photosynthesis. So, what are advantages of solar fuel technology? Hydrogen or carbon based feedstock such as carbon monoxide and methane could be produced from sunlight, water and carbon dioxide. So, this would provide an alternative to natural gas, oil and coal as raw material. Solar energy would also replace fossil fuel derived energy in the production process. Okay, what we can understand now. So, if we pay attention about artificial photosynthesis, what happens? So, this process mimics nature with inorganic semiconductor materials that are able to split a water molecule into oxygen and hydrogen using the energy of sunlight. So, input is sunlight and then we have artificial photosynthesis, then product is solar fuel like hydrogen or maybe carbon based fuel, okay, and finally we have transportation fuel or raw material for industry or maybe electricity generation, what we have already understood, and this is the pathway of artificial photosynthesis from sunlight to fuel. So, what are the challenges in artificial photosynthesis? So, first challenge is integrating the different processes and materials involved, from capturing and channeling sunlight for producing chemical fuels. And then second challenge is identifying inexpensive catalyst to drive different aspect of the process, and third challenge is developing ways to avoid the system degradation. So, now let us discuss about water splitting. So, what happens for storing solar energy as chemical energy in the form of hydrogen? Water splitting can be used. So, where this water is split to hydrogen and oxygen. So, already we have discussed the energy required for this reaction is given by Gibbs free energy, and it has a value of about 237.2 kilojoule per mole. This solar water splitting, the energy required for water splitting is come from sun. So, there are different methods of water splitting. So, one is electrolysis of water and other one is photoelectrochemical water splitting. So, now let us learn about electrolysis of water. So, this method is known as Hofmann voltmeter lab scale method. What happens? There are three tubes. First tube is cathode and then this tube is anode, and in between we will have water reservoir. So, this has to be filled with time, and initial energy required will be supplied from this solar array. So, at the anode reaction will be, this water will split to oxygen and proton, okay, and this will be in the electrolyte, okay, and this will be retained in the anode. And at the cathode, what happens, these protons react with the electron and it produces hydrogen, and overall reaction will be something like H2O split into oxygen and H2, okay, or hydrogen. So here cathode material is platinum and has an overall potential of about 0.07 volt, and anode material is nickel and overall potential of about plus 0.56 volt, and here is the cathode is minus 0.07 volt. So if we combine these two voltages here and here, the over potentials, we can understand that the typical over potential is usually around 0.8 volt. For an over potential is of 0.08, then an efficiency of around 60% will be there in that conversion system, and if we consider the PV conversion efficiency is 18%, then solar to hydrogen efficiency will be multiplication of 0.18 and 0.6. What we will get is about 10.9%. Okay? So if we have over potential of 8 volt and under that condition we will get an efficiency of 60% for the internal process, and then if we consider PV efficiency of 18%, then overall efficiency will be 10.9%. And quickly let us learn what is photoelectrochemical water splitting. So the photons reach the surface of the photoelectrode, this is a photoelectrode which is made of a photoactive semiconductor. It creates electron hole pair. The electrons and holes will be separated by an electric field, and both will be used in the two half reactions involved in the overall water splitting process. Okay? To generate the required electrical field, a voltage source is required, and this voltage source is nothing but solar PV energy. The photoelectrode can be either an anode or a cathode, okay, which is shown here. Okay. So this is about band gap of this photoelectrochemical water splitting process. Okay. So you can see the band gap of different level. So requirements for semiconductor material for this photoelectrochemical water splitting are, it has to absorb the light that is incident on its surface, the charge carrier transport inside the material, and the separation into the two electrodes must be efficient. It has been estimated that materials with an energy band gap close to 2.1 electron volt have the potential to split water. The energy level of the reactions have to be located somewhere in the energy band gap of the semiconductor. To further enhance the reaction, a catalyst may be added to the semiconductor surface. It is important to use materials that are photochemically stable and relatively cheap. And also have a look about the IV characteristics curve of this system. So this is the current density and this is the open circuit voltage, and if you see photoanode, it goes something like this. So this cross section point is considered, and this is the current density and this is the potential. Okay? And this is the operating point of the system. and the overall solar to hydrogen conversion efficiency can be expressed something like this. Okay. So, this is the current density, which is milliampere per centimeter square, and we will have this 1.3 times into volt, and P in is the irradiance arriving at the PEC. Okay. So, here this conversion efficiency is a function of current density. Okay. So, higher the operational current, that is current density, the more hydrogen is produced and the higher device efficiency. So, if you can increase this value, then it is expected to get higher overall solar to hydrogen conversion efficiency. So, there are some challenges in large scale production of solar fuels. What are different challenges? Is the efficiency. So, how to increase the efficiency of those systems, then durability. So, lifetime has to be increased, and third point is cost effectiveness. So, how to reduce the cost of the system. So, let us summarize what we have discussed today. Primarily, we have discussed emerging cell technologies, which includes perovskite solar cell, organic solar cells, dye-sensitized solar cells, quantum dot cells, and also we have discussed photovoltaic thermal technologies. What is the need? What is the importance of this kind of technologies for enhancing the electrical efficiency, and also we can get thermal energy out of it. And also we have studied the different techniques for harvesting solar energy as a solar fuel. So, thank you very much for watching this video.